Hello everyone. In this tutorial, we will demonstrate how to combine adaptive mesh Poisson solver with Schrödinger solver to model quantum confinement effect in nanowire quantum dot. This approach will provide a more accurate representation of electronic behavior in nanometric structure. In classical model, a statistical model treating electron as a classical gas which can lead to inaccuracy in nanometric structure due to neglect of quantum confinement effect. This simulation aims to model quantum confinement effect, improve accuracy over classical model, define a quantum dot region, solve the nonlinear Poisson equation, analyze energy level and eigenfunction. Before moving to the simulation part, let's learn about key terms used in this simulation. Let's talk about a nanowire and quantum dot. A nanowire is like a very thin wire, much thinner than a human hair. It is so small that its diameter is measured in 1 to 100 nanometer, which is a billionth of meter. Nanowire can be made from various materials like silicon, metal, or even insulating materials. If you talk about property, its high aspect ratio means the nanowire is much longer than its width, making it ideal for tiny devices. If you talk about quantum confinement, in a nanowire, electrons are confined in two dimensions, leaving one dimension for conduction. If we talk about quantum dot, a quantum dot is a tiny particle, even smaller than a nanowire, where electrons are confined in all three dimensions. Quantum dots are typically 2 to 10 nanometer in diameter, smaller than the wavelength of visible light, and its properties are discrete energy level. Quantum dots have a specific energy level similar to atom, which is why are sometimes called artificial atom, and strong quantum confinement. The strong quantum confinement of electron lead to unique optical and electronic properties. If we talk about cross-section of nanowire, it has two concentric cylinders. The inner cylinder is filled with silicon and outermost layer is gate, which is made of metal, and in between silicon dioxide is present. And we should talk about cut plane along the channel. The one end is source and the other end is drain. In between channel is present. In simulation, meshing means divide the device into smaller region for calculation purpose or computational purpose. Adaptive meshing means the mesh adjusts itself automatically to be finer in area where the solution changes rapidly and coarser in area with slow changes. If we look at the diagram, in the left image, it is a normal mesh, and in right image, it is a coarse mesh with a smaller region. And if we talk about quantum confinement effects are essential for understanding the electronic property of nanowire quantum dot. By solving Schrödinger equation with the quantum dot region, we can accurately model the effect and get insight into the behavior of confined electrons. Simulation, the two solvers are being used, Poisson and Schrödinger solver. Poisson solver calculate the potential in semiconductor device. The Poisson solver take into account is describe an electrostatic potential distribution in system, and its role in simulation is used to self-consistently solve the potential and charge distribution in the nanowire, ensuring accurate modeling of the electrostatic environment. Let's talk about Schrödinger solver. The Schrödinger solver deal with quantum mechanical behavior of electron in the transistor, and its purpose to govern the quantum mechanical behavior of particles such as electron, and its role in simulation is applied within the quantum dot region to capture quantum confinement effect, providing accurate energy level and eigenfunction of confined electron. To unlock the full potential, we need QTCAD tool, which is used for next generation transistor design. Now let's talk about key step to run the simulation. First step is geometry and mesh generation. First, we create the geometry of the device. Then we will start by generating the initial mesh using Gmesh and the provided geometry file. After that, we use device and Poisson solver setup. Next, we'll set up the device and configure the adaptive mesh Poisson solver, ensuring that the quantum dot region is defined correctly. After that, solving the Poisson and Schrödinger equation. We will solve the nonlinear Poisson equation self-consistently and use the result to define the confinement potential energy for Schrödinger equation. After that, we analyze the result. We will analyze the energy level and eigenfunction obtained from the Schrödinger solver and visualize the result. Let's talk about the workflow of QTCAD software. First, we create device specification where we create the geometry of the device, shape, dimension. After that, we create mesh with Gmesh software. After that, we run QTCAD where we define material, doping, and solver. After that, we analyze the result using PyPlot, PyVista, or Parabeam. Let's jump to the code. As you remember from the workflow of QTCAD, the first step is create geometry of the device, where we define device dimension, shape. I created earlier with the name of nanowire adaptive geo. Let's open with Gmesh software. I placed in C drive with QTCAD folder. Then example, tutorial, message, and nanowire adaptive geo. If you look at the geometry file, it has two concentric cylinders. The inner cylinder is filled with silicon and the outermost cylinder is silicon dioxide. And the one end is source and the other end is drain. And it's 1D structure. Let's visualize with physical tags. Surface volume, surface level, volume level. Then with physical names, gate band, source volume, channel volume, drain band, and in front source band. It created two mesh file with name geo unrolled file and mesh4 file, which is stored in same folder where geometry is placed. QTCAD, then example, tutorial, message, and it created two files, nano adaptive geo unrolled file and nanowire adaptive mesh4 file. As you remember from the workflow of QTCAD, the third step is done the simulation where QTCAD comes, where we define material parameters, device creation, mesh show, and solver being used, and analysis of the result. Let's jump to the BS code. We have some important module from QTCAD device package like constant as a city for universal physical constant like elementary charge, Planck constant, Boltzmann constant. Import classes and mesh and submesh from the mesh 3D module, which is responsible for the 3D meshing in device simulation. Mesh represent the entire computational grid for the simulation. Define the spatial discretization of the device symmetry into small element. Submesh, a subset of the main mesh useful for the defining a specific region of the device such as material, boundary, or electrode that require finer control or separate simulation parameter. Put the IO module, which typically handles input-output operation. Import analysis module, likely used for the post-simulation analysis. Extracting critical device metrics such as electric field, carrier densities, and current. Import the material module and consider as empty. Define material property for the device simulation such as semiconductor, insulator, and conductor. After that, we import device module from QTCAD device, which represent the complete simulation structure, combine geometrical, material, and physical property into a unified framework, provide method for a setting of simulation such as Poisson or Schrödinger solver, sub-device, a smaller modular component of the main device, enable hierarchical modeling of complex structure like MOSFET may have sub-devices for the gate, source and drain. Import the solver class from the Poisson module and consider as a Poisson solver essential for computing electric field and potential distribution in semiconductor device. Import the solver parameters class from the Poisson module. Define parameters for the Poisson solver such as convergence criteria, boundary condition, salt tolerance and step size. Import the solver class from the Schrödinger module and analysis at Schrödinger solver used for quantum confinement effect and energy level calculation in nanoscale devices. Import the path-lib module, part of a Python standard library for the file system path manipulation. Handle path in a platform independent way. Create, read, or write file directory. Define some device parameter where gate source voltage is 2 volt. After that, we define metal work function where electron affinity and band gap. After that, define device height in nanometer, device radius in nanometer, device height in 20 nanometer, and device radius is 2.5 nanometer. Significance of these parameters are VGS determine the operational point of the device, EW metal work function ensure compatibility between the metal gate and semiconductor material affecting the threshold voltage, and has total device height affect scaling behavior and electric field distribution, and radius influences both electrical and thermal performance in nanoscale devices. After that, we define part to the mesh file and output file, where skip directory, path live.path, and parent resolve. After that, we define path mesh and path geo with nanowire adaptive mesh 4 file, nanowire adaptive geo unload file. After that, we load the mesh scaling in nanometer, and after the mesh creation, we create device from the mesh and set temperature to 10 millikelvin, where carrier is electron and set temperature in 10 millikelvin. After that, we create device region where channel oxidation, source oxidation, and drain oxidation, where material is silicon dioxide, and channel source and drain, where material is silicon and source and drain is p doping. After that, we create device boundary like source band, drain band, and gate band, where gate source voltage is 2 volt and metal work function apply. After that, define the dot region as its list of region level in between channel and channel oxide. Set the dot region in which no classical charge is allowed. Configure the nonlinear Poisson solver and set the tolerance, initial reference factor, and final reference factor. After that, create an adaptive mesh nonlinear Poisson solver. After that, we create self-consistent solution. Then plot the band diagram. Then get the potential energy from the band edge for uses in the Schrödinger solver. After that, we create some mesh including only the dot region. After that, we use create a Schrödinger solver, solve Schrödinger equation, and print the energy function. After that, we plot the three eigenfunctions ground state, first excited state, and second excited state using analysis.plot slices. After that, we define the xy plane for the slice and plot the first eigenfunction in 10 nanometer plane. We created 3D mesh statistics. After that, solve Poisson equation with boundary condition. Again, some Poisson iteration happen. 27 Poisson iteration occurs. It created a band diagram where red color show conduction band, so valence band, and in between Fermi level. And in y-axis, energy in electron volt and distance in nanometer. It created the submesh where the dot region present, ground state, first excited state, second excited state. Here our simulation completed. In this tutorial, we revisited the nanowire structure, focusing on the interplay between Poisson and Schrödinger simulation. In analyzing the quantum dot region, we examined how the conduction band is from a potential well and how classical and quantum approaches influence the result. By incorporating Schrödinger equation within the quantum dot region, we highlighted the importance of considering quantum confinement effect in nanoscale devices or structures. Thank you for watching. See you in the next video.